announcement. I know I wrote this down last time, but there is 3 to 4 open slots for this study group. They meet every Monday from 9:30 to 11. It's supposed to let you know it's not a drop-in session or a lab, but instead, if you sign up to attend these sessions, you're expected to attend each session every week for the duration of the semester, and the tutors take attendance. So it's pretty, you're pretty locked in, but it's a good resource. If that time doesn't work for you, you know, if there's like 3 of you, 2 of you, or 3 of you, or 4 of you, you can also form your own study group at a different time. So I do want to remind y'all that that service is available. I'm not saying that anybody needs a study session or anything like that, but it is available, 3 to 4 open slots, or you can start your own. So she didn't imply what room it was.
It's L248.
L248?
Yeah.
Okay. Oh, that's the same one? Okay. So this is L248.
Okay, sorry.
All right, so do y'all have any questions on the homework? Yes?
Number 11.
3.1, number 11. Okay, so number 11, 3.1's homework. It says for the function and the point below, find f prime of a. What is f prime of a? What is that going to give us?
The derivative.
The derivative
Point on the derivative.
at this value, x value of 1/4
Yeah.
on the function. And what does the derivative give us? What is the derivative describing? It's the slope of the tangent line. Yeah. So it says find the slope of the tangent line on the given function at a equals to 0. So really the methods in 3.1 were using the one or the two formulas for finding the derivative at a point. And then what we saw in 3.2 was we got another formula that gave us the derivative function that allowed us to find the slope of the tangent line at any point. So, you know, on the exam, I would assume that you're going to use the shortcut that we start looking at in 3.3, 3.4, 3.5, 3.6, or 3.7, etc. But, you know, for now we have one of those 3 formulas, okay? And I suppose since it's in 3.1, we should perhaps use the one of those formulas instead of finding the derivative function. I will say, maybe let me back up. I will say that it's more important to be able to find the derivative using the definition than it is using the derivative at a point formula from 3.1. Okay. So with that in mind, let's look at that just so we can have another example. So we'll use the definition of the derivative function from 3.2. And that was the derivative function f prime of x was defined as what? Who remembers the definition?
Of x plus h minus of x over h.
Okay, good. Yeah. That is the definition of the derivative. We're missing what?
The limit as h approaches 0.
Yeah, the limit as h approaches 0, but that's really just the difference quotient. Once we tack on the limit as h approaches 0, now we have the definition of the derivative. So when you have to compute something via the definition, we're going to find what f of x plus h is, and then put it into this definition, simplify our difference quotient, and then compute the limit as h goes to 0. So our function is 1 over root x, or we could call this, I don't know which one's more conducive, but x to the negative 1/2. We could write it that way as well. I think since we've seen a few examples of how we clear radicals, that we'll probably keep it as 1 over root x. So we're going to compute f of x plus h, which gives us 1 over the square root of x plus h. Now, as far as computing the limit, again, I don't really care if you simplify this quotient by itself first and then put all of that in front of the limit, or if you just keep the limit as h approaches 0 throughout your computations. 6 and 1, half a dozen and the other. Doesn't matter. Whatever you prefer. Okay, so we're going to compute or simplify our difference quotient with the given information. So just be mindful, the difference here versus 3.1's formula, 3.1's formula had the a's in it. So once we knew what a was, we just plugged that into the formula and started working with it that way. Here, what we're going to do is first find the derivative function, and then once we find that function in terms of x, we're going to plug that x equals to a equals to 1/4 in for that. So we have 1 over the square root of x plus h minus f of x, 1 over root x, all over h. So this one actually poses two problems that we've seen individually but not together, right? So we have complex fractions involved and we have radicals involved. So suggestions on what to do here to simplify that. Okay, lowest common denominator. So 1 over root x wouldn't quite do it for us.
Multiplied by root x plus h
Yeah.
times x.
So we're going to multiply this by the denominators, root x plus h times root x. So we need to do that on the bottom as well. And that way we can get rid of the complex fractions and see maybe if that will be helpful to us. So multiplying out the numerator, what would I get?
Root x.
This was just the root x minus root x plus h, and then still over this. Remember, we don't want to multiply or try to simplify the denominator, because the problem is that h is going to 0. We need to get rid of that in the denominator.
So would that be a common conjugate?
Yeah.
I feel like it did that.
Okay.
Maybe I was just doing algebra wrong.
Okay. Yeah. Let's see what happens here. So now we have no more complex fractions. We do have an expression that involves radicals. So at this point, we would introduce the conjugate of the numerator. So we're going to multiply all of this by root x plus root x plus h. And in all honesty, it's probably easier to do the one of the two formulas from 3.1 to find the derivative at a point, but here we are. Okay, So the denominator is going to get sort of tedious. I'll just go ahead and write this out. Okay, and what does the numerator turn into?
X.
Yeah, so this, let me write it here. The numerator, we have root x times root x, and then we have minus the product x plus h. Is that right? So what do we get up top?
Negative H.
Then a negative h up top. Don't forget to distribute that negative. I think that's probably, with these, after you've done a few, that's probably the most overlooked step is that negative in front of this second term. It gets distributed to both of those terms, not just the x.
Could you eliminate the h in this one?
Yes, at this point, exactly. We've got an h divided by h, well, negative h divided by h. So that leaves us with a negative 1 all over this stuff on the bottom. I'll just write it out in there. There, that was lazy.
And then just that H. That H right there.
Okay. Oh, I can't. Oh, let me group them. Whatever. All right. I'll just erase that. But that's our simplified difference quotient. Does anyone have any questions on that? We have to then compute the limit as h. Sorry, that h is all on the bottom is gone. We have to compute the limit as h goes to 0. Any questions on where we're at now, though? That's the bulk of the problem, is simplifying all that. Okay. Okay. So as h goes to 0, we have, that's right, negative 1. This is square root of x times the square root of x times the square root of x plus the square root of x. So what does that turn into? Is what? 2x squared? This is x. Oh, let me erase that. This is x, and this is
2 root x.
2 root x. So let's combine those as a power, because I mean we could leave it like 2x root x, like that. I don't really think there's anything wrong with that. Or we could say that this is negative 1 over 2 times x to the 1/2, right? So we can actually combine those x's as a power of x. And negative 1 over 2 times x to the 3/2. Just add their exponents. 4, you can say that's negative 1/2 times x to the negative 3/2. So how you represent this from this step to either one of those three, I think is sort of irrelevant. I'm really not looking for, can you represent it in a particular way? Especially with this problem, because the goal is to find the derivative at the given a value. So now find f prime of a, which is f prime of, I believe that was a 4th.
Yep.
Yeah. So now we need to find f prime of 4. And what we know is f prime of x is negative 1/2 x to the negative 3/2, or however you want to represent that. We just need to plug in 1/4 to that function. Whichever one of these you want to use. Okay. Anybody have any questions about that? All right, so what is negative 1 over 2 times 1/4 to the 3/2? Negative 4. Anybody else get negative 4? So any number to the 3/2. Is that number cubed? Take the square root of that number. So that's just the square root of n number times number times number, which we know is the number times the square root of that number, right? Some number to the 3/2 is equal to. So 1/4 to the 3/2 is 1/4 times the square root of 1/4. So that's an 1/8. So we have negative 1 over 2 times 1/8. Negative 1 over 1/4, which is negative 4. All right, so it's a sort of a long-winded process, but what do we know? What does all of that work for?
The slope of and tangent is
Yes. Okay, so on this function, 1 over the square root of x, at the point 1/4. So at this point right here, we know that that function is, the steepness at that point is negative 4. The slope of the tangent line is negative 4. That was all of that work to find that. I promise once we look at shortcuts from 3.3 and a lot of sections onward, that finding derivatives will be a lot easier. You still have to remember like how to take a derivative depending on what the function is, but we move away from computing this limit on the difference quotient, and it makes things a lot easier. And then to determine the equation of the tangent line, then that's just our point slope formula. So I'll leave that for you. Negative 4 times x minus 4. So you need to find that point. That y value is just f of 1/4. And then you've got your equation for your tangent line. Anyone have any questions on that? All right, other homework questions? Yeah.
I'm working on 3.2, so I'm not sure if you're too far ahead.
All right,
I got
check
a
it out.
question on number 9.
Okay, so we've done that. That's actually exactly what we just did. So you would, I mean, it's not the same function, right?
Right.
But it is a little simpler because we don't have the fraction and the radicals. We just have the radicals.
You just do conjugate.
So the conjugate, yeah, to simplify the difference quotient. So it looks like you would have 3 times x plus h plus 7 plus the square root of 3x plus 7 as your conjugate. You're multiplying that on top and bottom. So since it is so similar, I don't want to work it in class. If you have issues, like, please let me know. I'll email you or something.
Homework is time consuming.
It is. Yeah.
Smart as hell.
Yeah. Yeah, I mean, you see, like, the importance of time, right? The homework takes a long time to go through, especially if it's your first go-round.
It's not hard, but
It's-
damn, it's time consuming.
It's time-consuming, yep. If it's not hard for you, I think that's a good step, right? But the term hard is relative to the user. Yeah, I remember working full-time and going to junior college or community college full-time for 2 years. It was probably like some of the hardest days of my life.
Good time.
And then I go into debt to not work during undergrad, which was awesome because I could just focus on school, but then you leave and you have this huge debt you have to pay off, and it's kind of depressing. But please continue with your education. That's not to deter you.
Is that what we're looking forward to?
Hopefully y'all can get scholarships or have a rich benefactor pay for your school. You never know. Okay, so 3.2, what we left off talking about, outside of how to find the derivative function, was how do we graph the derivative. And so we're going to look for these 4 things here to determine what the graph of the derivative looks like. A lot of times these graphs aren't going to be exact because you don't have specific values to compute slopes. And it would be highly inconvenient to compute slopes at all points. Just impossible to do. So where the slope of the function, the given function f of x is positive, and you just imagine putting your pencil on there. Is the slope positive or is it negative? Depending on what that tangent line is doing, that determines where you're going to draw the graph of the derivative. If the slope is positive, you have the part of your derivative above the x-axis. Slope's negative, the graph of the derivative is below the x-axis. Where your slope is horizontal, the tangent line is horizontal, your derivative will have zeros or x-intercepts. And where the function is undefined, a whole or vertical asymptote, you'll have something funky going on with your derivative. And we looked at these 4 instances. They're really just 3 different ones. 320A and B are illustrations of the same concept, which is a vertical tangent. Corners and discontinuities, holes, jumps, those kinds of things. So we've got for examples, given the graph of a function, we want to graph the derivative. So looking at this function f of x, hopefully what jumps out at you is, well, f of x has two corners. I know the derivative at those locations isn't going to be defined. But what else we notice about the function is that it just consists of 3 line segments. So the tangent line on any linear function that's mx plus b, what would the slope of the tangent line be? The slope of the line, right? So, like if you're visualizing that, hopefully this one's pretty easy to see that if I put my tangent line at this point, then it's going to be this line here. The tangent line at this point is, again, this line. At this point, it's this line, right? So no matter where you construct your tangent line, the slope is always this, whatever that is. So since we have these tick marks here, we can actually measure the slope of that line. So what is the slope of this line here?
-1.
-1. Does everybody agree with that? Just down 1 over 1. Okay, that is the slope of that particular line, but what does that mean about our derivative?
That it's below the x-axis, one space, and it's a flat line.
Right, yeah, so our derivative is constant, because the slope, our pen is on that, it's always doing this. The slope of your tangent line is always -1 on that line segment. So if the slope is always -1, the derivative is always -1, your derivative is constant. It's not varying. So let's try to line this up the best we can. And label this. These are still our x values, but what we're graphing here is f prime. So our outputs are the derivative, or our outputs are the slope of the particular function. So I don't know, let's say here is -1. The slope is constant throughout. So I'll try to just draw this straight. But what happens to my derivative once I reach this point on the function itself? So it would jump, right? Because the function to the left of it has a different slope. But what do we know about the derivative at that corner?
It's not different.
It's not defined, right? But if we were super, super close to this corner, let's say right here, what's the slope of the line, or the derivative very, very close to that point?
-1.
It's still -1, right? So this is an x value of 2. So that just means here this x value of, -2. At this x value of -2, we're going to indicate that the derivative is undefined. Right? We wouldn't have, okay, this thing outputs -1, -1, and when it gets here, it's still outputting -1, right? Because we know the derivative is not defined at -2, so we indicate it with our removable discontinuity. Is everyone all right with that piece? Yeah.
Just real quick, so from there, do we pick up as a slope of 1 from -2?
Yes, because after this point, then we pick up here with this line, and we ask, along that line, what's the slope? What's the derivative? It's 1. So since this slope is +1, and always +1 on that segment, yeah, so what do we know on this side where the slope is 1? Here and here, The graph of the derivative has what? Yeah, it's not defined there. There's a hole. So here at -1, from an x value of -2 to an x value of 0, the slope is always 1. So again, the derivative is just that constant function. Again, not defined at -2, not defined at 0. The third piece, our third line segment here, what's the slope of this line? -2? Yeah, so down 1 over 2. Down 1 over 2. So that derivative on that line segment is always -1/2. Notice that line segment here, again, starts super close to this x value of 0, but it's outputting -1/2. We know that this is also not defined here as well. So that's the graph of that function's derivative. Does anybody have any questions on that? Any of your graphs that consists of just line segments, like even your absolute value graph, will just consist of horizontal lines. The derivative will, undefined at the corners. So I don't know if this is helpful or not, but we can just visualize the slope here. And then when we get to that point, since the slope dramatically changes here from -1 to +1, that's why it's undefined with those removable discontinuities, and that's why we have that jump, because the slopes rather jump from -1 to +1 as soon as we round that corner, if you will. Same thing here. So I don't know if that's helpful to view, kind of playing out, but that's kind of what we reasoned through anyways. Does anyone have any questions on that graph? All right, so the other ones we have don't actually deal with line segments. So here's the graph of g of x. So I'm gonna put this. Yeah. And then here we'll graph g prime. So with the curves, what I would recommend first is finding any place that you have a horizontal tangent. So are there any locations on G where we have a horizontal tangent?
Yes.
Okay. Well, where are those?
On
0? No, sorry.
They're on the peaks and the troughs.
Yeah, the peaks and the troughs, right? So here at this point, looks like an x value of -3. At this point, x equals -1, and at x equals +1. So at all three of those spots, those locations, we have a horizontal tangent. So I'll fix that. I don't know. That's straight. That's straight. And that's straight. Horizontal tangent, horizontal tangent, and horizontal tangent. So just, again, maybe you can imagine your pencil just traveling along this path, and it gets here, it's flat again, and then it's flat again, right? I hope that's pretty easy to visualize. So if the slope or if the derivative is 0 at those locations, then what does that give us actually on the graph of the derivative?
Intercepts. X-intercepts.
It gives you where the function is 0 or your x-intercepts. So we've got an x-intercept on the graph of the derivative at -3, at -1, and at +1. So the slope of the tangent line is horizontal, which means it's 0 here, here, and here. Okay, then it's like any other graph that you've had up to this point. What's happening to the left and to the right of the zeros is how we're going to look at this now. Okay. Does anyone have any questions on that? The idea of a horizontal tangent is very important, especially as we move into chapter 4. Because remember in algebra when you were graphing a polynomial and you said, all right, well, the polynomial has a 0 here and a 0 here, and I know based off the multiplicity that it crosses and then it touches. Y'all remember doing that kind of stuff? And then if you didn't plot points that are somewhere in here, there was no way to tell where that, that peak, those peaks and those troughs were, right? So you just kind of had to like wing it. Okay, it does that. I'm not quite sure exactly where that's at. But what we can do with calculus is we know that the slope at all those peaks and troughs, the slope of the tangent line or the derivative is 0 there. So if I can find all of the points on the function where the derivative is 0, then I know exactly how high those and how low those things go. So it does come up very frequently in chapter 4. All right, let's focus on this piece right here. We're just looking at pieces to the left and to the right of our zeros. So if we're on that blue portion, what are our slopes doing? They're positive and what?
Increasing.
So they're positive, would they be increasing or decreasing?
Decreasing.
They're decreasing, why?
Because it's getting smaller. Your functions.
Yeah, they're getting flatter, right? They have to get closer and closer to our horizontal tangent in green. So, pick a point here. This line right here is really positive. The slope of this line is really positive, but the slope of this line, not so positive anymore, right? And then the slope of this line at this point, and then the slope of the line at this point. But all of those lines have a positive slope and they're decreasing to 0. So we just illustrate that on the graph of the derivative. We have positive slopes, which means our graph is going to be above the x-axis on the derivative, and they're decreasing to 0. So, really positive slopes getting smaller and smaller towards 0. We don't have any y values to calculate anything, so we just, get as close as we can. Are there any questions about that portion of the graph and its derivative? Okay, so then after our 0 here, on this piece of our function, what are our slopes doing? They're decreasing? Well, they start out pretty much at 0, right? So then we look at the slopes of these lines. Are these the slopes of these lines on the red graph, the red part of the graph, are they positive or negative? All of these lines have negative slopes, and then they're getting less negative, right? Well, they start out flat, and then it's like it's a little negative, and then it gets more negative, right? And then it gets less negative, back to 0. So, we're just kind of following the slope of our pen as we move across that line, negative to 0 again. So they start out a little negative, get more negative, and then get back to 0. Is everybody able to see that? So they're a little bit negative, more negative, and then they have to come back to 0. Okay, and this third piece, what are the slopes doing here? Right. Yep. I don't know, I don't have that color. So we start out kind of right here. They're positive. They get more positive, and then they have to flatten out again.
This is basically the same graph but flipped over the y-axis.
Not quite. They start out positive, they get more positive, and then they flatten out to get to 0 again.
Is it positioned differently? Because the spot where it zeroes out is the peak on one of those, and then it's just a spot on the other.
Yeah, the x-axis. It's the
It's not exactly because of that, but is there a term that defines what this is called?
in particular, what do you mean?
I have no idea what I mean. Like, it's not mirroring because it's not mirroring over the axis, but creating that version of the graph that's what's defining the derivatives of that one. Is there a name for that type of graph, or?
We would just call this graph here that we would just call it the graph of the derivative.
Okay.
Yeah.
So the points on the derivative that are the peaks and the troughs, are those the inflection points of the graph above it?
Yeah.
They are?
Yeah.
Okay, cool.
We haven't talked about that,
Okay.
so
No, that's fine.
but it's perfectly acceptable to make that connection since you know what it is. Absolutely. Yeah. All right. So there's that thing. How about this last piece? What are the slopes doing there? They're negative, and then they're getting more negative, right? So at this point, it's pretty negative. At this point, it's more negative. At this point, even more negative. So after that 0, they're negative, getting more negative. We'll just do that. So that's the graph of our derivative. Of course, it's all one thing, so maybe ignore the colors, but I think that's, hopefully they help in determining how we got each portion of that graph. Does anyone have any questions about that?
How do you know which way the line is sitting?
On the tangent line? It's
When
just
you're
based
moving
off the
up to
curve.
flat line.
I just imagine like a ruler traveling along this function. Like those are all your slopes at those particular points. I mean, I think that's the easiest way to explain that. So like at this point, what is the slope of the tangent line? Well, if I put this here, then it's positive, right? I wouldn't say it's negative. I wouldn't look at it like this because I'm reading my graph from left to right. So as I start over here, I'm kind of looking at the slopes unfolding this direction, not this direction. Does that make sense? I don't know if that's helpful, but.
I know what you mean.
All right, so here's another visualization. Again, that red line is, we're just tracing out the slope along g of x. Then we have it's flattening out there again. Just getting more negative. So I don't know if that's helpful for you. These interactive figures are available to everyone. They're just in the textbook. So there's many ways to get there, but I think the fastest is the multimedia library. And you select Chapter 3, Section 2,
and select interactive figure, and that'll pull up all the interactive figures for this section. So if you're like a visual learner, not everything has an interactive figure, but for the visual learners, I think that when something does have an interactive figure, it can be really helpful. All right, so everybody good with that derivative graph? All right, so I'm gonna let y'all try this one.
We'll get started by saying, though, that this function has vertical asymptotes at 1 and -1. So will your derivative. All right, why would that be the case? This is F. This is F. Well, what happens to your function, what happens to the slope of your function, rather, as we get closer and closer to the vertical asymptote on f of x? Right, they approach infinity in some direction, right? They're either positive or negative infinity, but the slope close to the vertical asymptote is pretty much vertical. Okay, so from the given graph the derivative of f.
Her name is sarcasm. Her superpower is the razor sharp edge of sarcasm. Yeah, like I'm gonna fight you.
Let's think about this.
So at the beginning, it's a negative, but it's very shallow, so it's very small, which means it starts at a negative, but just below the x-axis.
So basically that's what it's like.
Yeah, so it's basically exactly.
The same line.
Yeah. But once you get to the other side of the asymptote, it's going super negative, so it starts super negative and gets shallower and shallower until it.
So if you're stuck, first try to find if there's any horizontal tangents on the graph of f of x. Anywhere there's a horizontal tangent, you'll have an x-intercept on the graph of your
Here,
derivative.
so it's going down here, but it's also going way down here. So it comes down.
There's not specific values, so just, you're just eyeballing this again.
And it crosses into positive. Here it's positive, then it crosses over and it's negative. So then these two pieces are basically the same. So then this here.
I feel like that
Okay, so check this out. So if you come to slope here, it would be something like negative heads, which means this point here goes negative. That's when it's decentralized. Graph kind of changes it all. It doesn't just round sound.
It would actually.
Yeah, that's the connection.
There's only one function you should graph because the function and the derivative are the same.
I was like, yeah, that makes sense what he's saying.
So, so just think about that piece on the far right. Yeah.
So like, the tangent will be horizontal somewhere in here. Now, right, the entire example, you might want this function has to cross the x-axis here because it'll have a this is flat.
I'm not quite.
Yeah. That's a little bit of
It'd be high risk.
Yeah. It'll cross on the negative side.
But if you got it,
Either you fail it.
Because this one negative.
just go to lower.
No, because when you draw everything out, you're saying avoid that middle and then the slopes on that are positive.
Because it looks like it is.
So you have
It's going to hit and bounce back.
Yeah, but see, like if I'm going from left to right, if I put my pencil right here, instead of
Yeah, it goes down, down, down,
Right.
down.
So since these slopes here are negative, the graph
Already
derivative
says
needs to
to
be
me, he's working 11 to 8. And typically when you work 11 to 8,
Yep.
you go on break at like 3 or 4. And then sometimes on break at 1.
Probably come over here like that.
Yep.
I'm not good at drawing.
Yeah.
It's only break.
Yeah, was that the guy that like, yeah, okay. I was thinking of a guy on PBS that was like, draw.
Yeah, slam it. Drawing.
It's
Old enough to party.
hours you have to take 30 but if you were
Yeah, so like this, for instance, this would have looked like this. All of these slopes are negative.
but it's up to you whether
Since this is sort of, the graph of the derivative has to be. I mean, is that negative? Does that make sense?
There's a lot of
Yeah.
And then that's also like
increases
different
50.6.
industries have different rules around them as well. So like for us, it's like in some other high intense industries they give you a 30-minute and then a 10-minute. But with us, it's either the paid 10 or the unpaid 30 unless you're working 12 plus hours, in which case then you're entitled to 2 credits. But we're also like super lenient in terms of like your health. So like I have a guy who works for me who does as a full-time apprentice as an electrician and also works what we consider full-time at 30 hours with us. And so I typically get him unpaid 30 and unpaid 10. But I don't make him register as paid 10 because then it's like docked for that. So I just let him go sit down. Because usually he just needs to go sit down for but then it gets really weird especially because we hire at 15 and that's how we really get into lots and lots of roles. I'm a manager at Culver's, so I work in the service. And then my boyfriend works at Culver's too, and we originally started at the same store. But there was pretty easy sense of boss. But we were dating before I was even hired, so when they hired him, or like from a beginning, they hired him together. So that's why I was like, but they moved him to the Littleton store that they just opened under our same owners. It's a franchise. But he is now leaving the company altogether because he's still not getting promoted, still not getting a raise. They made him safe certified, which is food safety training with the they paid for his they didn't pay him for and they just like, it's just like little things that are just like weird. And so he was supposed to make some hour with traffic. And so he's now waiting to show plus target. He originally was going to go work for Target Optical, and they'll start.
They're like robots shorting out. That's supposed to happen.
And so now he thinks he's just gonna go with I'm staying strong at Culver's though, because I make pretty decent money, and I don't have to like solid in my job. So plus I have I make $1.90 every year. Ending.
This is my.
I was like, I know conceptually.
Well, that's kind of where it's at, is like everyone receiving a 96.
They have trucks for
But the issue is, which I found surprising, they'll bump up their minimum price, but not everyone. Yeah, I bumped them too.
I think it's totally
The thing with that is, we have a guy who's
using the wrong way. Once you got to it,
Dude, I have to arms and legs.
Yeah, I make like 14 and I get
Over here, these lines are very negative.
but it's based on how much that's how I or a little bit less than
I've just done what they are.
so it's a person, our bonus is broken into half. We receive 10% up to, so I got 45%. They had exactly how they calculated how much my bonus was.
Which isn't even good on the speed.
Like my normal time plus 18 hours overtime
last half of it was like,
Football team or anything like that. My bonus check was $1 and pretty this one
My bonus was $600.
I still don't know the
At 45%. I don't know, I really like where I work, and my owners are really transparent about everything. And then the company is also I've yet to find, I thought, and maybe they're just like really hiding it, but I thought I was.
I would really like to have everybody.
Oh, okay. Yeah.
Like, literally, this is what comes out. Start doing it like, because so many problems, especially if they just would evaporate instantaneously because everybody has some knowledge. Or, everybody can look at it and go, we're over here and Bob, the CEO, why is he making 900 times? You would have solid numbers and you go, okay, there's a problem here. We have two options.
Well, we are also.
Yeah, he's,
Actually,
This would actually cross before the original. Right, but other than that, looks good.
And I don't know success.
give me my money.
But why do you need 500? So
I know why I need 500. I'm typing thinking about buying this one.
They offer.
It's a spicy. Well, I'm about to hit Chrissy's checkout because I'm ready for it. 6 feet long.
How wide is
It literally is just over 14 years. Oh. Yeah. So you can.
You would start going into like signs and stuff.
Am I about to check out? Because I have charcoal brushes, a ton of
Wait, you better. He didn't use it.
that would be my value cutoff right there.
Well, okay, because it's the
It's an algebra based.
We're not selling.
I was saying, the brushing looks like typical.
Yes, so, for somebody
That's a wonderful.
when you start.
It's also.
Yeah.
All right, there's a graph of our derivative. So I'm gonna run through their interactive figure here. So they're really flat, getting more and more negative. So the derivative has to be down here, and they're very negative, flattening out, getting more and more positive. Then it's really negative, getting flatter and flatter, or closer and closer to the x-axis. Okay. I don't know why it disappeared, but there you go. That's what we ended up tracing out. So just, look over that. If you still have questions on that, then please ask. Can we look at the last example, then take a break?
Sure.
Yes, sir.
All right.
Yeah, sure.
Okay. So this is g of x or graph g prime of x. Big oof.
Big oof. Big Minecraft.
G prime. All right, so we'll focus on this piece here on the far left. On this piece, what's the derivative? It's negative, right?
Negative.
But does it ever vary?
No. No.
No, so again, on a line segment, your derivative will always output a constant. So since we don't have the y values to actually measure the slope of the green line, all we know is that it's positive, right? So it's just going to be some constant. M is some positive number. It's always that positive number. So it'll look something like this, right? Just a flat line. Derivative is always positive. And whatever that slope is, maybe it's 1, maybe it's 2. So notice the difference between the derivative on a line versus the derivative when it's 0, right? So the derivative at like peaks and troughs, we plot it on the axis itself as a point. Okay. Well, what happens when we get up to the next value of -2 on this line segment? It jumps, right? So we have to illustrate that our derivative is undefined there. Where your derivative is undefined at corners, vertical tangents, and discontinuities, be they holes or jump discontinuities.
So whether it's a closed hole or an open hole, it doesn't matter in the sense of the graph of the derivative?
It would matter, yeah. So we include that point on the graph of G, but the derivative doesn't include that point because we can't define a derivative somewhere where the function is just terminates like that, right?
Even though it's a closed hole?
Right, even though it's defined on the function. So the derivative was defined as h approaches 0, so the derivative is like a two-sided limit.
Okay.
So that, that may be worth mentioning here, like, something like this. We say that the derivative here is 0, or the slope of the tangent line is 0, because whether we approach this from the left or whether we approach that from the right, think about approaching it simultaneously. Those things are going to get flat together at that point. When we have something like this, there's no way to approach that point that's included on the function from both sides. So since that two-sided limit doesn't exist there, you can't define the derivative as the slope from both sides anymore. Okay. All right, then we're going to pick back up here. Is the derivative defined here? No. So again, that's an x value of -2. But if we were super close to that removable discontinuity in blue, what would the slope of the tangent line be? 0. It'd be pretty much 0 right there, isn't it? It's pretty much flat, even though it's not identical or on top of that circle. So we've got an open circle on our derivative, and that's pretty much 0. Or flat. The slope is pretty much flat there. So back to the x-axis to draw that. Undefined at -2. And then what do our slopes do after this? They get more and more negative, right? What happens there at that cusp?
Undefined.
It's undefined because the slope of your tangent line is getting more and more what? Negative or vertical, right? So we're approaching an infinity, but they're all negative. Right. So these slopes are really negative, just getting more and more negative. We pick up on the sort of the right side of this cusp. Again, these are vertical. It's a vertical line right there. That's an infinite slope. But then after that, what do our slopes start doing? They're decreasing in the sense that it's positive infinity. But then it's getting closer and closer to 0, a flat tangent line at an x value of 2. So here we'll say here's our x value of 2. The slopes are pretty much 0 there, but again, the derivative is undefined. Okay. Started out at infinity. It's positive infinity because those slopes on the red are positive, and then they approach 0. So they start out way up here at positive infinity, and they approach 0. Okay. To the right of the hole, what are these slopes doing? Decreasing, or they're all negative, right? They start out pretty much flat, and then they're getting more and more negative. So whatever that looks like, just something to that effect.
So that hole, using the pen for the slope, that's not necessarily accurate all the time?
Yeah, it is. In what sense are you thinking that it's not?
Because if you follow it just like with a pen or what have you, the slope is positive.
Which piece in particular, the red?
From 0 to 2.
Okay, right. Yeah, these slopes are all positive.
Right, but we have it going. Are we making a negative? I guess what direction is that line?
See, all we're looking at is this is G prime, and since it's above the x-axis, these are all, this is indicating that they're still positive, right? Because these are all positive values. Like, I don't know, maybe that's positive 300 or something, right? So even though this is falling down, it's decreasing, it's because we started out vertically and then we ended up flat. So we started out very, very large, and then we got to 0. So we start off very, very large, and then we get to 0, like that. So that's you can measure like whatever that y value is. Maybe it's 10,000. That's the slope right here. So again, moving from left to right, we start off vertical, positive, 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 then it's 0. We start out vertical, and it has to decrease because it starts at infinity and ends at 0. It's decreasing. But the slopes are still positive. The graph is still above the x-axis because those slopes are positive.
So that line is reading from right to left, not left to right.
Yeah, from left to right. As we go from here to here, what's happening?
If it's reading from left to right, you're decreasing on the y-axis. Wouldn't that indicate a negative slope?
The derivative has a negative slope, but the function doesn't have a negative slope. We're saying, what is the function doing in order to get the derivative? We're not looking at what the derivative is doing to get back to the function. I mean, we can, but that's a different process.
So wait, for the pink one, it's not below the x-axis?
Yeah, it is. I need to get rid of that stuff.
Okay, I was like, what?
Yeah, the pink
Okay.
portion is below because they're 0 and then getting more negative. The 0, the pink part, it's 0 and then they get more and more negative, which is why it's below, the graph of the derivative is below the x-axis because these are negative slopes.
So a trick I like to use to try to keep this straight in my brain is I will just pick random places and figure out kind of what the slope is. Like it's positive 5 here,
Okay.
which that's a position down in your derivative.
Okay.
So if the slope is positive 5, that means it's at positive 5 on the y.
Right.
And then if
Yeah.
it's positive 10, then it's positive 10 on the y, and then you can actually plot out where it's going.
Yeah, so I mean, that's kind of what we're looking at without having to look at all slopes. But let's just say the slope of this line, let's say we measure that to be, I don't know, negative 10. Since the slope of the curve, G prime, since G prime is negative, or sorry, since G is negative here, the derivative, let me say that again, I'm getting messed up. G has a negative slope, so the derivative is negative 10. So over here we would say, okay, well here's negative 10, then that particular slope corresponds to that particular point. And then we'd say, all right, well what's the slope here? Maybe that's negative 35. And so at that particular point, this output here is negative 35. And so, I don't know, if you're going to look at it as a point-wise thing, that could be helpful too. But the negative slopes correspond to negative outputs, because these, on the y-axis here, these are the slopes of our tangent lines. I don't know if that helps. But yeah, thanks for interjecting. Yeah, so I don't know, just maybe we can talk after break or during break if it's still kind of unsettling.
Yeah, it just doesn't seem consistent.
I assure you it is, but it's just a
Yeah,
matter of like
yeah.
how we're gonna look at it so we can, configure it in our minds.
Do we write so that where V's in the middle and then it pretty much will have just a straight line, tangent line?
Yeah.
Do we write that as a vertical asymptote in the derivative or no?
Yeah, so the V's or the corners,
Right.
you'll have a jump from one value of the derivative to the other, but with cusps where it gradually gets more and more vertical, like that, then that'll be an asymptote, because you have a vertical tangent here. Here, it's not that you have a vertical tangent, it's just this slope is -1 and this one's +1.
Right.
So it jumps from -1 to +1. Yeah. Anybody have any other questions? I know it's kind of weird at first because we're not used to looking at graphs in terms of their slopes. That's all we're doing to graph a derivative. I know that's overly simplistic, but all right. Well, how about we take a break and then we'll come back and finish.
They have a certain amount of bandwidth, and you can
Okay. So the following theorem might help with graphing derivatives as well. But the theorem states that if your function is differentiable at A, what does it mean to be differentiable at A?
Edge?
No, not an edge. Differentiable is associated with derivative.
If the derivative exists.
The derivative exists, right? So to be differentiable means that the derivative is defined at A. So if a function has a derivative that's defined at A, then that means the function is continuous at A. So that's the theorem. Differentiability implies continuity. There's an alternate version, but the slight detour is just sort of it's applying to logic. If you've ever had like a logic class in like philosophy or whatever, a lot of times in math when you see a theorem, they like to present it in an alternative way. So there's a statement, there's the converse of the statement, and there's a contrapositive of a statement. So statement, if today is Thanksgiving, then it's Thursday, that's a true statement. The converse of that is when you just flip the conclusion and assumption. So the converse of the statement is, if today is Thursday, then it's Thanksgiving. Then that's not true, right? So it's invalid, right? Because the next time we meet will be Thursday, but it's not going to be Thanksgiving. So it's not a true statement. The converse isn't. But the contrapositive is when we flip the statement and we negate both things. So if today is not Thursday, then it's not Thanksgiving. So we take the converse and then we just negate both of those things. The contrapositive is a true statement. If you have a true statement and you look at the contrapositive of that statement will also be true. So the contrapositive of a true statement is always true. You really don't have to remember any of this stuff. It's just there to understand sometimes like why we see theorems presented in certain ways. So if I say a function is differentiable at A, means that the function is continuous at A, and I take the contrapositive of that, I can say if the function is not continuous at A, then the function is not differentiable at A. So the alternate version of theorem 3.1 is simply the contrapositive of theorem 3.1. That's the contrapositive of theorem 3.1 stated in this alternate version. If it's not continuous, then it's not differentiable. They're saying the exact same thing. Okay, and so maybe that notion or that theorem can help with when you graph derivatives as well. Because in theory, we should know about continuity. So what is not true is the converse of theorem 3.1, and so what is the converse of theorem 3.1? Well, we just take the assumption and conclusion and flip them. So the converse is not true. The statement is then the converse of 3.1. If a function's continuous, then it's differentiable. So the converse, if f is continuous, we'll just have to abbreviate that. If f is continuous at A, then f is differentiable at A. The converse here, this statement is false. Make sure you don't get these things confused. Differentiability implies continuity, not continuous implies not differentiable. So to help you to remember that just because a function is continuous doesn't mean it's differentiable, just think about the absolute value graph. We have our absolute value. So as far as differentiability and continuity, if you can just remember this graph, maybe that can help you keep these concepts straight. The absolute value graph is continuous at A. Equals to 0. 0. But is it differentiable at 0? Does the derivative exist at 0?
No.
No, why not?
Because it's a corner.
Because it's a corner. So it's not differentiable at A equals 0. So if you can remember that graph, then you can say, okay, well, I know it's continuous but not differentiable. So just because a function is continuous at some place doesn't mean it's differentiable. And the absolute value is the example to sort of reinforce that. If it's not continuous, it's not differentiable. But continuity doesn't tell us anything about differentiability. Anybody have any questions? Differentiability implies continuity. Not being continuous implies not being differentiable. So however you want to think of those, both of those are accurate. The statement that we wrote down here is not accurate. Okay, so we'll come back to this example. Where is the function g of x, A, not continuous, and B, not differentiable? So let's say, so part A, g of x, we'll say g of x is not continuous. At x equals to what? Negative 2 and positive 2. Okay, do y'all agree with that? Why is the function not continuous at x equals to 2? Yeah, there's a hole in a jump, but in terms of continuity, what is happening?
Yeah, like the whole limit of f of x is not equal, let's say.
Right.
That rule.
The function is defined
It's failing that rule.
at negative 2, but remember continuity checklist number 2, the limit has to exist. So the limit as x approaches negative 2 on g of x does not exist. Why doesn't the limit exist?
Because the limit of f of negative 2 is not equal coming from the negative and the positive side.
Right, exactly. So the limit doesn't exist because our one-sided limits aren't the same. Why is the function not continuous at x equal to 2?
Because f of 2 doesn't exist.
Right, because the function's not even defined there. So that's number 1. F of 2 does not exist. All right, so that's more appropriate. Okay, so g of x isn't continuous at x equal to negative 2 and positive 2. So again, by the previous theorem, the alternate version says if the function is not continuous somewhere, then that automatically qualifies it for not being differentiable.
What about like that first graph that we did where it was just like straight lines, but all of them were sharp turns? Would that whole graph still be continuous?
Yes.
Because even though there's angles.
Yeah, this graph is continuous everywhere, but it's not differentiable at the corners. Yeah. Okay, so for part B, immediately by Theorem 3.1, the alternate version, we know that the function is not differentiable. G of x is not differentiable at those two locations. Okay, just from that theorem, the function is not continuous, the function is not differentiable. Is there any other x values on g of x where we can't define a derivative?
X equals 0.
At x equals to 0, why so here?
Tangent line has an infinite slope.
Right, because we have an infinite, our tangent line has an infinite slope, so you have a vertical tangent there. So the function is also not differentiable at x equals to 0. But we don't get that particular x equal to 0 from the theorem. So again, I hope this example sort of reinforces that we have not continuous means it's not differentiable, but just because we're not differentiable at a place doesn't mean the function's not continuous at that place. Okay, do y'all have any questions on that? Okay. So we're done with 3.2. 3.3 is where we start getting the shortcuts to take derivatives. So. All right, the first theorem is dealing with a constant. So a constant f of x equals to c. It's always a horizontal line. What's the slope of the horizontal line?
0.
It's always 0. So the derivative, the slope of the tangent line on a constant function is always 0. I guess we should introduce, we haven't talked about this notation, have we? I don't know when they talk about that. Seems like they should have mentioned that already.
It starts popping up in 3.2.
Okay, so I'm just going to go back to 3.2 and make a new page. If they're going to introduce the notation, I think we should talk about it. So the notation for the derivative. There's many different ways to notate the derivative. There's 3 primary ones that we see. One we've already seen with the definition, which was f prime of x. The other notation for derivative is dy over dx. So if you remember exactly what the derivative was, we said, look at the slopes of the secant line. And then we make one point closer and closer to the other. So this second notation is I think, really indicative of what a derivative is. Just view this d as a super small change. It's a really small change in y over a really small change in x. So that's all a derivative is. It's a change in y over change in x, but it's a specific change in y over x. So small. Change in y, small change in x. And then, that of course just gives us a slope. In general, if we say, what's the change in y over change in x, you get a slope. We know this is a specific kind of slope. And then the other one is the derivative with respect to x, and then they'll have some function in here. It says take the derivative with respect to x of the function f of x. Or take the derivative of f of x with respect to x, however you want to word that phrasing, phrase that wording. So those are the three primary notations for derivative that we see. All right, there's a detour. So the derivative then of a constant function is equal to 0. How do we identify a constant function with respect to x?
It has no variable on it.
It has no variable x on it. So if the question was, take the derivative with respect to x of 5, there's no x there. So with respect to x, 5 is a constant. If it said take the derivative with respect to x of w plus z, there is no x there. W and z, in terms of x, they are constants. So this derivative would also be 0. So no x, it's constant with respect to x. Okay. Next rule is the power rule. So it tells us how to take the derivative of x to a power. And sort of the way the textbook introduces this rule is it's refining what n is. So notice here as it's presented, it says the derivative of, with respect to x, of x to a power n, where that power is some non-negative whole number. 2, 3, 4, 5, 6, 7, 8, etc. But as you go, as chapter 3 progresses, they present this rule like 2 or 3 different times, and they're just modifying what that power can be. So we're not proving any of these theorems. So let's cross out n is a non-negative integer, and just say n is a real number. So it says to take the derivative of x to a power, you bring the power out front to multiply x and then reduce the power by 1. So for example, it says that in order to take the derivative of x squared with respect to x, that we put the power out front to multiply x, and then we take 1 away from the original power. So we have 2 times x to the power of 2 minus 1, which is 2x to the first. So already you can see it's much more efficient than computing the limit on the difference quotient. What's the derivative with respect to x of x to the 5th?
5x to the 4th.
5x to the 4th. Now imagine if you had to put that into the difference quotient. You had to take x plus h, multiply itself 5 times, subtract off x to the 5th, simplify all that, right? That's super tedious. Okay, so that's our power rule. By the way, most of these sections in chapter 3 deal with derivative rules or shortcuts, and they come in very quickly, and there's a lot of them. So I would recommend that perhaps you keep some sort of note card or flashcard where you have, a function and its derivative on the back or something. You need to keep up with these derivatives because there's a lot of them and they come really, really quickly. So in 3.4 and 3.5, we look at how to take the derivative of a product and a quotient, and then how to take the derivative of a composition of two functions. So then you add all the functions right? Power functions, trig functions, inverse trig functions, algebraic functions. Then you start multiplying those things together and dividing those things and composing those things. You have a whole slew of functions to deal with. So the better, the more quickly you can get these derivative rules down, the better off you're going to be. And it's probably just something you should look at 5 minutes before you go to bed every night. Yeah.
I don't know if you guys know about this, but this is a little reference quick guide. Got it for $4 at the bookstore.
Okay.
It had everything that we need for. It's like a menu, but for calculus.
Yes,
So
delicious.
it's really awesome. Yeah.
It's just super.
Yeah.
Yeah, it was $4 or something. I got the used version. It was $1 less.
Okay. Yeah.
But it's not Barnes and Noble. It has the Spark Notes, calculus guide. Pretty sweet.
Okay. Yeah. Those can be super useful. For sure. Yeah. Thanks.
For chemistry too.
Okay. Next theorem, constant multiple rule. It says what happens if we have some constant times a function of x. And notice this is different than just taking the derivative of a constant. It says the constant can be pulled out and we can compute the derivative and then multiply in the constant. So for example, what is the derivative of, with respect to x, of 2x to the fifth?
10x to the fourth.
Yeah, the derivative rule says we can take that constant that's times the function of x out of the derivative operation and just take the derivative of x to the fifth. And then we would say that's 2 times 5x to the fourth, which is 10x to the fourth.
Is there going to be a time where using the constant multiple rule is more efficient than using the power rule?
No. I think usually once you get these down, most people just say, well, the power rule says the 5 has to come out front and multiply.
Right.
So it's just 5 times 2 is 10, then diminish the power by 1. I think in practice that's usually how it works.
Is there a reason that they differentiate them?
Yeah, so if you have more complicated functions that have constants in them,
Right.
times the function of x, sometimes it can be a little bit more beneficial, I think, to pull those out. Right, I'll end up erasing this. But if you had to take the derivative of 1 over 2 times the square root of x,
No.
I think it might be a little bit more efficient to take the 1/2 out and just take the derivative of 1 over the square root of x.
Okay.
How do you take the derivative of 1 over the square root of x?
You just change it to x to the -1 and then use the power rule?
Yeah, exactly. So radicals or reciprocals of any radical all default back to the power rule, right? So 1 over root x I would write as x to the -1/2 and just apply the power rule to take the derivative.
Now with the power rule, does the negative, when you're using that, when you have any kind of x power in general, does the negative multiply times the coefficient and also stay in the power?
Yeah,
Or is
you still have to reduce the power by 1 though.
Okay.
Yeah.
It would still be negative 1/2. You'd be multiplying the coefficient of the 1 that's not real, it's not technically visible.
Right.
But you would still be using negative 1/2 minus 1.
Yes.
Okay.
Correct. Yeah. So let's go back up here and look at that if we can. I don't have enough space, but yeah. So let me erase this and then.
I guess just more so of like, you know, I guess the only reason I asked that is just to see if how it matches against, like factoring. You know, with factoring, if you take a negative, you sometimes have to switch the sign inside the parentheses, et cetera.
Oh, right.
You know what I mean?
If
But
you
in
take
this-
it out of both.
Right, exactly,
Yeah.
but in this case, it's just staying static.
Right.
Okay.
Yeah.
So let's look at an example. Take the derivative of 2 times, take the derivative of 2 times the cube root of x. Well, let's do 2 times 1 over the cube root of x. So this is, you know, once we start dealing with all of these derivative formulas, it becomes very crucial to identify what my function actually consists of. Because what your function consists of tells you what derivative rule you need to use. So 2 over the cube root of x, the 2 is a constant, it's just 2 times that function of x. So the 2 can actually come out. To multiply 1 over the cube root of x. Right? Does everybody agree with that? Is that clear? And then we can say, well, I don't know how to take the derivative of a quotient. And even when we look at the quotient rule, it's a lot less efficient. Anytime you see radicals involving x, or whatever variable, you always turn those into powers. So what's the power associated with 1 over the cube root of x? Okay, x to the not positive 1/3.
Negative 1/3.
Because it's on the bottom, it's negative 1/3, right? So x to the negative 1/3 is the same as 1 over the cube root of x. And this is just a power rule, so we have the negative 1/3 comes out to multiply x, and then we take 1 away from the power. So we have to do negative 1/3 minus 1, or minus 3 over 3, times that. Okay, so then we have 2 times negative 1/3 x to the negative 4/3, which is negative 2/3 x to the negative 4/3. So some of these derivative rules, that you know, it is lengthy sometimes to take a derivative, but always in the back of your mind, just keep the derivative rule as opposed to the limit process in mind, and you'll appreciate the derivative rules a lot more. All right, Theorem 3.5, the sum rule. If I have to take the derivative of 2 functions of x added together, and we can go ahead and modify this or add to this. We know subtraction is just addition of the opposite, so this really does take care of addition and subtraction of 2 functions. So the derivative of a sum or difference is the sum or difference of the derivatives. In other words, the derivative operation will distribute across sums and differences. So for example, the derivative of, what's the derivative of 2x cubed plus 3x squared?
6x plus 6x.
6x squared
Oh, 6x squared.
plus
6x.
6x, right.
That's 1x squared.
So that says that we can take the derivative of 2x cubed and then add to that the derivative of 3x squared. So power rule with a constant for both of those. First one's derivative, 6x squared plus 6x to the first. Second one. Does that make sense? Anybody have any questions on that? I think the last rule for now in this section is the derivative of e to the x is e to the x. So it's the only function whose derivative is itself. So we've got a few rules here. Next section we get more. The next section we'll get another one. The next section another one, and so forth and so forth and so forth.
Yum.
So keep in mind, what does the derivative tell us?
The slope of the tangent line.
The slope of the tangent line. What's the physical interpretation of a slope of a tangent line?
The instantaneous rate of change.
Instantaneous rate of change, yeah. So we spend a lot of time just taking derivatives. So just always keep in the back of your mind that when I find a derivative that will describe the slope of the tangent line at any point, or it will describe the instantaneous rate of change at any point. Okay, so write the equation of the tangent line for f of x equals to 2x minus 1/2 e to the x at the point 0, negative 1/2, and then find the points on the graph of f of x where the tangent line is horizontal. So for part A, we've seen a few of these examples. For the equation of the tangent line, you need a point, which we have, and you need the slope of the tangent line at that point. So the first thing we're going to do is find the slope of the tangent line, which is f prime of x. So notice we have to take the derivative of 2x minus 1/2 e to the x. You don't necessarily have to write what I did here on the right-hand side. Just, again, make sure you're labeling things. Like if you take a derivative, label it as the derivative.
So like in that example, like right there, is there a more, I think the best way to describe this? Essentially, I guess, for the derivative of our 2x, when we make that derivative, and I'm assuming it'd be 2 minus 1/2 e to the power of x.
Right.
Would you then, is there a better practice, or is it a better practice to leave it as such, or should we combine the 2/1 minus the 1/2 to make it a singular fraction times e to x?
So you couldn't actually combine. Let's find the derivative first, and then we can address what you're talking about.
Okay.
So the derivative is the derivative of a constant times a function of x minus another constant times another function of x, right? So again, you don't have to write all of this stuff out, but I'm just going to illustrate at least this first example through through our theorems. Okay. So with the derivative distributed across the sums of difference, we have our. Let me see how much space I have. A lot. So then we have our first term, the derivative of 2x. The constant 2 times a function of x, 2 gets pulled out. We have just the derivative of x minus here, constant gets pulled out, multiplies the derivative of just e to the x. Is everybody okay with that? I think the more of these you do, the less you'll have to break this down and think of them, this way. So what is the derivative of x?
2 or 0. It would just be 1.
It's just
be 1, 0.
Yeah, the derivative of x is just 1. So you have 1 times 2, which is 2. So the derivative of x, we're thinking about that as just x to the first. So that the power comes down to multiply x to the 0. X to the 0 is 1, so you have 1 times 1, which is 1. Minus 1/2 times the derivative of e to the x, which is what? E to the x. Derivative of e to the x is e to the x. Okay, so that's our derivative. And so I think your question was, would we take that a step further and combine those?
Right.
And for here, the answer is no, because they're not like terms. One's an exponential and the other one's just a constant. So we couldn't combine those two together. So there's our derivative. That function gives us the slope of the tangent line at any point on the given function 2x minus 1/2 e to the x. So we're asked to write the equation at the point, equation of the tangent line rather, at the point 0, negative 1/2. So the slope of the tangent line at 0, negative 1/2, how do we find that?
Plug 0 into the derivative.
Yeah, exactly. So our x is 0 for this point. We have the derivative function. All we need to do is evaluate the derivative at the x value of the point. So f prime of 0 is 2 minus 1/2 times e to the 0. What is 2 minus 1/2 e to the 0? 1.5, right? That's 2 minus 1/2. So on the given function at the point 0, negative 1/2, it has a slope of 3/2. Anybody have any questions on what we've done? The equation of the tangent line. Y minus the y coordinate, slope of the tangent line times x minus the x coordinate. X minus 0, I'll write that, x minus 0. So 3/2 x minus 1/2. So that's the equation of the tangent line. At the point 0, 1, negative 1/2. Theorem, let's just grab this here. So there's original function given. We wanted to know how steep is it at this location. We said it's 3/2 x minus 1. I wouldn't have to have you graph these things on the exam. I think it's just good to verify visually that what we did is accurate. Does anyone have any questions on that? Yeah. Yeah, sure. So we are a little bit behind. We might not get to every single example that we have in the guided notes. So we will have to pick up the pace a little bit so we don't fall further and further behind.
like I said,
I would definitely start writing these derivative rules down or going over them almost on a daily basis. There's going to be a whole lot of them. Yeah.
So what's the answer to the last part of the problem, where
Well,
the tangent line
yeah,
is horizontal?
for part B, we'll have to look at that on Thursday,
okay.
because I need to pass your exams back.
That's right.